Everything around you is made of tiny things called atoms. Think about the chair you're sitting on, or the air you are breathing, or even your own body. It's all atoms. These atoms don't just sit still. They are constantly interacting with each other. They bond together. They break apart. They swap partners. When atoms rearrange themselves to form new substances, we call that a chemical reaction. It's like a grand microscopic dance where atoms are the dancers. It's an incredible ongoing process that makes everything in our world possible, from baking a cake to launching a rocket into space. Consider this. You mix vinegar and baking soda. What happens? It fizzes and bubbles. That's a chemical reaction in action. They are turning into something new. Carbon dioxide gas, water, and a type of salt. And one of the most important, most fundamental types of chemical reactions is something called a redox reaction. It sounds complicated, but I promise it's something you see every single day. So what is this redox thing? It's a name that is actually a combination of two words, reduction and oxidation. They are partners. They always happen together. Let's break it down. Let's start with the basics. The key is tiny, negatively charged particles called electrons. In many chemical reactions, atoms can either lose electrons or gain electrons. It's all about where the electrons are going. Remembering which process is which can be tricky. Chemists have a clever mnemonic. All you have to do is remember this phrase. Leo-ger. Leo, loss of electrons is oxidation. Ger, gain of electrons is reduction. So Leo gives, Jar takes. A friendly lion reminding you which is which. Now let's look at a real-world example of a redox reaction. Rust. Think of an old bicycle, a chain, a nail left outside in the rain. Over time, that shiny, strong metal turns into a flaky, reddish-brown substance. That substance is rust. On a microscopic level, iron atoms lose electrons and oxygen atoms from the air take them. According to our mnemonic, the iron is being oxidized, Leo. The electrons transfer creates a new substance, iron oxide, which we call rust. The result is weak, crumbly metal. This is why rust is a problem for structures and vehicles. It's all because of that unstoppable transfer of electrons. Let's dive a little deeper into this idea of electron exchange. This is the heart of every redox reaction. Atoms exchange electrons to reach greater stability and release or store energy. Electrons move from places where they are less comfortable to places where they are more comfortable. Think of it like a waterfall. Moving downhill releases energy that can do work. This movement of electrons releases energy that drives processes and powers devices. The substance that causes oxidation is called the oxidizing agent, the electron grabber. The substance that causes reduction is the reducing agent, the electron giver. That sounds odd. The oxidizing agent itself is reduced, and the reducing agent itself is oxidized. Where else can we see redox reactions at work? Look at the battery in the palm of your hand. A battery is a controlled redox reaction in a can. It forces electrons to travel through a wire so we can use their flow as electricity. Inside a typical alkaline battery you have zinc and manganese dioxide separated by an electrolyte. Zinc wants to lose electrons, LeO. Manganese dioxide wants to gain them, GeR. But they are separated so electrons can't jump directly. The battery has a negative terminal connected to the zinc and a positive terminal connected to the manganese dioxide. Electrons build up, waiting for a path. When you put the battery into a device, you complete the circuit and create a path for the electrons to travel. Electrons travel out through the wire, power the bulb, and return to the positive terminal where they are accepted by manganese dioxide. This continues until zinc is used up, or the manganese dioxide can't accept more electrons. Then the reaction stops, and the battery is dead. Rechargeable batteries use external electricity to force the reaction in reverse and push electrons back to their starting points. A battery is simply harnessing electron flow to do work, a clever use of redox chemistry. Redox reactions are absolutely essential for life, for thinking, moving, and breathing. When you eat food, like a piece of fruit containing glucose, your body breaks it down to release chemical energy. Cellular respiration oxidizes glucose in a series of steps, transferring electrons along a chain and releasing energy that cells capture as ATP. Glucose is slowly oxidized. It loses electrons in steps. Oxygen you breathe in accepts those electrons and combines with hydrogen to form water. Cells capture this energy in ATP, the rechargeable battery of your cells. Once you start looking, redox reactions are happening everywhere, in your home and around the city. Bleach works through oxidation. Sodium hypochlorite pulls electrons away from dye molecules, changing their structure and removing color. Burning, like a match, a campfire or a gas stove, is a rapid redox reaction where fuel is oxidized and oxygen is reduced, releasing heat and light. Cut an apple and enzymes oxidize phenols to brown pigments. A reducing agent like lemon juice, vitamin C, protects the fruit by getting oxidized first. Redox shows up in photography, water treatment, chlorine oxidizing contaminants, and metal smelting. These electron transfers connect seemingly different processes: spoilage, power, corrosion, photos, and life itself. Understanding redox gives you a new lens to view the world, a hidden dance of electrons everywhere. So, there you have it. Redox reactions are the simple story of giving and taking. One atom loses electrons, oxidation, another gains them, reduction. Remember, Leo the lion says GR. Loss of electrons is oxidation, gain of electrons is reduction. Same fundamental process, different outcomes. Rust weakens metal, batteries harness flow, your cells harvest energy to keep you alive. It's not magic, it's chemistry, it's redox. Now you know the invisible dance of electrons. Science is cool, keep looking for the chemistry all around you.